Hello, everyone, and welcome to today's lecture. Today, we're going to be talking about graph traversal. It's going to be part two of the lecture that we started last time. So this is part two for this chapter. But before that, let's quickly review what we covered in the last lecture. So in the last lecture, on part one, we started by introducing what graphs are, and we observed that the graphs can be represented as adjacency matrices, which are sparse matrices, and these sparse matrices can be represented using the sparse matrix storage formats that we discussed in the previous lectures. So we can represent the graph using CSR, using CSC, using COO, and each one of these representations gives us kind of a different accessibility into the graph, right? COO helps us parallelize across non-zeros. So for every non-zero, we can figure out its source and its destination vertex. CSR helps us for a given vertex find all the outgoing edges, and CSC helps us for a given vertex find all the incoming edges. And then we said that when we parallelize different graph traversals, there's different ways of doing the parallelization. There's a vertex-centric parallelization where we assign a thread to every vertex to do something for that vertex. And usually that involves iterating over the outgoing or the incoming edges. So we usually use CSR or CSC representation for that. Or we can have an edge-centric parallelization, and an edge-centric parallelization involves assigning a thread to do something for every edge in the graph. For that, we usually use something like a COO representation. And for some algorithms, not necessarily BFS, but for some graph algorithms, we may need to have both accessibilities. Given a vertex, I want to look up the endpoints, but then also given given an edge, I want to look up its endpoints, but then also given a vertex, I want to iterate over incoming or outgoing edges. So in these cases, you might want to use both a COO and a CSR and or a CSC representation at the same time. We use BFS as an example, and we said that we do one level at a time, where in each level we take all the vertices. So here, when we're looking for level 2, we want to look at all the vertices that are in level 1, and we want to mark their neighbors as being in level 2. And to do this, we can apply the vertex-centric approach, where every thread is assigned to a vertex. And again, there's two versions. There's the push approach, where we iterate over outgoing edges, or there's the pull approach, where we iterate over the incoming edges. In the push approach, we assign a thread to every vertex, and the thread that happens to have a vertex that's in the previous level, level 1, will iterate over the unvisited neighbor. It will iterate over all the neighbors, and the ones that are unvisited, it will mark them as being in level 2. And then we had the pull approach, where we also assign a thread to every vertex, but then the threads that are assigned to unvisited vertices, these threads will iterate over their incoming edges, and will if any of the incoming edges are in the previous level, they'll mark their vertex as being part of the current level. We also said that the push and the pull approaches have different strengths and weaknesses. And that's why there's usually the push is good in the early stages where we haven't visited a lot of vertices. Pull is good in later stages where we have visited a lot of vertices. So the chances of finding a vertex in the previous level among our neighbors is high. So the direction optimized approach will start with the push approach and then switch to the pull approach. We also looked at the edge-centric case, and in the edge-centric, we assign a thread to every edge. And what that thread does is it will, if the source vertex is in the previous level and the destination vertex has not been visited, it will mark the destination vertex as being part of the current level. And we saw that the edge-centric and the vertex-centric pull approach are usually better at dealing with load imbalance than the push approach. However, the advantage of the push approach, and we'll quantify that today, is that it will only iterate over the neighbors of each vertex once. So it won't iterate over the neighbors unless those neighbors are, it will not traverse an edge unless that edge is relevant in that iteration. And for this reason, the better approach depends on the actual data set. So in graphs where you have high degrees of the vertices and also kind of a power law distribution where there's a lot of variation in the number of neighbors that different vertices have and the degrees of the vertices. For these graphs, usually the vertex-centric pull or the edge-centric approaches are better because they're better at dealing with load imbalance. On the other hand, with graphs that have low average degree, these graphs tend not to have a high imbalance, but they have a very large number of iterations, and in every iteration, only a small number of vertices are processed. So for these graphs, it's usually better to use the push approach. And again, we're going to quantify this in today's lecture. We also observed that there's a similarity between BFS and SPMV. And as a matter of fact, with a few tweaks, we can actually formulate BFS in terms of SPMV. And that's the case for many graph problems. Many graph problems can be formulated in terms of sparse linear algebra. And this is useful because if you want to kind of get started quickly with implementing some graph computation, if you can formulate it in a linear algebraic way, then you can use an existing mature, well-optimized library for linear algebra to have a quick and efficient implementation of the graph problem. Of course, the linear algebraic formulation is not always the most efficient formulation. So the disadvantage is that it's not always the most efficient way to solve the problem. However, there are many cases where the graph formulation, the linear algebraic formulation, does a pretty good job at accelerating the graph computation. So this is what we covered last time. Any questions about what we covered last time before we move on? Everything's clear? Okay, so then today we're going to continue with part 2 of this chapter. And we're going to start by talking about an observation that many of you made last time, which is that all these approaches perform a lot of redundant work, right? Many of you observed that these approaches that we discussed last time, we are launching a thread for the vertex-centric approaches. We launch a thread for every vertex on every iteration. For the edge-centric approach, we're launching a thread for every edge on every iteration, right? And many of these threads end up not doing anything because their vertex or their edges are not relevant to that particular iteration. Okay, so the approaches we discussed, they check every vertex or edge in every iteration. There's an advantage to this. The advantage is that it was very easy to implement. All our implementations last time were very simple, and they're highly parallel, and we don't have to synchronize across threads, right? By launching a thread for every vertex and every iteration and having that thread check that vertex for its relevance, I didn't have to worry about talking across the threads to check which vertices are relevant and which vertices are not, so that I only launch threads for vertices that are relevant. But of course, the weakness here is that I launch a lot of unnecessary threads. I do a lot of unnecessary work because a lot of threads will be launched. They'll check their vertex or their edge. They'll find that that vertex or edge are not relevant for this iteration, and then they will terminate. Okay, and to quantify this, right, let's consider if we have a graph with n vertices and m edges, and let's look at how much work is performed by each of these iterations. First of all, if I had a sequential implementation that did the least amount of work, how many operations would I need? How many vertex visits and how many edge visits would I need to do the whole BFS computation?
Isn't it n plus m?
Right, exactly, because in an ideal implementation, or the implementation does the minimum amount of work, I have to visit every vertex once, and I have to visit every edge once, okay? So in such an implementation, right, I would do O of n plus m operations, okay? So this is how this is kind of the baseline for our work efficiency. Now let's think of the vertex-centric push approach. And let's say that the number of iterations we have, or the depth of our BFS tree, is D. Okay? If I do D iterations, how many operations, how many vertex visits, how many edge visits do I do? Let's start with vertices. If I have D iterations, how many vertex visits do I do? D times n, right? Because I have D iterations, and in every iteration, I will check every vertex for its relevance. Okay, what about how many edges do I visit?
M only.
Each iteration will only visit the relevant edges, which means every edge is only going to be visited in one of the iterations, correct? So what that means is I will end up in total visiting the edges m times, right? So for the vertex-centric push approach, I have O of d times n plus m operations. Is this clear? Okay. What about the vertex-centric pull approach? In the vertex-centric pull approach, I'm also going to launch a thread for every vertex on every iteration. So I have d times n operations to visit vertices. What about edges? Is it the same?
It's upper bound by m, but it's not exactly m.
You're saying it's upper bound by m. What's upper bounded by m?
The number of edges visited
Per iteration or in total?
in total, because per iteration it's less than the all of the edges in the adjacency.
So let's think about this. Could I visit the same edge more than once in the pull approach? So you're thinking of the loop that has the break, right? But I can construct a case where we never break. Let's think of a graph that's a path, right? In a graph that's a path, right? I'm never going to break because every iteration I'm going to visit one vertex. Okay, let's think of worst case here.
That's why
in
I
a graph
said
that's a
it's
path, I
upper
never
bound
break.
by m, because there is a worst case that we do reach m, but chances are we'll break before m. Before
Right,
reaching
exactly.
m
Chances
vertices.
are we'll break before m. However, I could visit up to m vertices per iteration, right?
Yes.
Right? If we think of a graph that's a path, on the first iteration, I'm going to visit m edges. Second iteration, I will visit m minus 1 edges, m minus 2 edges, etc. So the number of edges that I will traverse is m times d, where d is the depth of the BFS or the number of iterations, right? Because if you think of the edges that get traversed in the last that get visited in the last iteration, I will be checking those edges every single iteration until I end up traversing them. Okay, so for the vertex-centric pull approach, it's O of d times n plus m. Now, of course, many of you observed that the benefit of the pull approach is that I end up breaking early, which gives me better load balance. But I do end up visiting more edges in total. It's just that those edges will be visited in parallel. Okay, and this should show you why for graphs that have a small number of levels with small d, the pull approach is better than the push approach because, well, small d and also kind of high degrees, right? So the small degree relative to the size of the graph, right? So graphs that have a small d, if you look at the pull approach compared to if you have a small d, then here, here I have a d times n plus m, here I have d times n, and then plus m without a d factor. So when d is small, the pull approach is better because this d factor doesn't create too much more work. On the other hand, I get the benefit of breaking early to get load balance. Whereas if d is very large, here, I end up doing a lot more work in the pull approach, whereas in the push approach, I won't do a lot more work, okay? And when d is very large, usually the average degree is small, so I have a lot of levels, but then I do a little amount of work in each level. So that's why the push approach is better, okay? What about the edge-centric approach? In the edge-centric approach, how much work do I do? So every iteration, I'm visiting all the edges. So it's O of d times m. Now, of course, when I visit the edge, I'm also checking the source vertex, checking the destination vertex. So in the edge-centric approach, right, I don't have a v here because I would actually check the same vertex multiple times, once for each edge. I check the same source vertex multiple times, once for each edge. And I will check the same destination vertex multiple times, once for each edge. So here, the edge-centric approach is O of d times m, but it has a bigger constant than the pull approach, for example. That's why don't think that edge-centric is doing less work than the pull approach because it's smaller. It's just that this d times m has a larger constant. Okay? So as you can see, for all of these, they're all, if you compare them to the O of n plus m, they are all not work efficient. Okay, why? Because of this idea of this D factor, because I'm visiting the same vertex and the same edge multiple times. So all the implementations are not work efficient. If I wanted to have a work efficient parallelization, what should I do? So if I want to avoid this redundancy, I want to make sure to visit every vertex only once and every edge only once. Okay? And if I want to visit every vertex, I don't want to launch a thread for all the vertices every iteration. If every iteration I only want to visit the vertices that are relevant for that iteration, what that means is that I need to somehow collect the vertices that are relevant for each iteration in some buffer, some array, so that I would only inspect those vertices during that iteration. Okay, and we call this a frontier. So to reduce the alternative to avoid this redundancy is we only want to check the vertices that are part of the previous iteration. So the approach is that for each level, we're going to add the vertices that we visited to a list so that the next level will process these vertices. And we refer to these vertices as the frontier. The frontier of at a level is basically the frontier of the BFS search is basically each level has its own frontier, which consists of the vertices that I need to visit at that level. Okay, so the advantage of this is that it reduces the redundant work, it improves the work efficiency. What's the disadvantage of this?
Synchronization.
Right, exactly. It's more complex. It needs synchronization because I need to coordinate across threads in order for them to insert their vertices into that frontier. Okay. So for example, here if I wanted to do a vertex-centric frontier-based BFS, in the first level, level 0, I would have this vertex. So I would actually have an array that's the previous frontier that consists of just this vertex. And then I know how big this array is, so I launch a thread for every vertex in this array, in this case, one thread. And that thread is going to iterate over the neighbors and insert their neighbors into the next frontier. Then the next iteration, this next frontier becomes the previous frontier. I will launch a thread for each vertex in the frontier. Those threads will iterate over their neighbors and enqueue the neighboring vertices in the next frontier. And then in the next iteration, this next frontier becomes the previous frontier. And again, I launch a thread for each one of these vertices. They iterate over their neighbors and they enqueue the neighbors in the next frontier. And then in the final iteration, I launch a thread for every vertex in the previous frontier. This thread will iterate over their neighbors, and then the next frontier is none of them will enqueue anything. And when I look and I find that my next frontier is empty, or the size of my next frontier is 0, that's how I know that the search has terminated. Is this clear? Any questions? Okay, so let's go and implement this and see how it works. I'm going to switch to the code. Okay, so over here, I've already set up a kernel for us. Excuse me. And in this kernel, I'm passing the same thing as before. There's the CSR graph. There's a level array that tells me the level of each vertex. But I'm also passing the previous frontier. This is an array of the vertices that are in the previous frontier. And then current frontier, this is an array of the vertices that are in the current frontier. This is the array that I'm going to be populating during this in this kernel. Num previous frontier tells me how many vertices I have in the previous frontier. I'm going to use this for the boundary check. Num current frontier is a counter. It's initially initialized to 0, and I'm going to be incrementing this counter in order for me to allocate space in the current frontier to insert the new vertices. And then finally, we have the current level. Okay? If you look at where this, how this code is being launched, so down here, I have the kernel that I'm launching, and then the number of blocks is determined based on the number of threads in the previous frontier. And this is something that I am copying from the GPU every iteration, and I keep iterating until this value becomes 0. Okay? Great. So I'm launching as many threads as I have in the previous frontier, plus, of course, some extra threads in the last block if it's not perfectly visible by the block size. Great. So the first step is to assign a thread to every vertex in the previous frontier, right? So I'm going to write unsigned int I is equal to block index.x times block dim.x plus thread index.x. Then I do a boundary check. If I is less than, how many threads should the size of the previous frontier? So num previous frontier. And then now every thread is going to go and load its vertex from the previous frontier. So here every thread grabbed an index, and the thread is going to go and load the ID of the vertex from the array that's the previous frontier. So here I'm going to write unsigned int vertex is equal to previous frontier of I. Is that clear? Any questions? Okay. Now, what does this thread need to do? Now, every thread wants to iterate over its neighbors and to find out if any of its neighbors are not visited. If any of the neighbors are not visited, it's going to mark them as visited. But then it also needs to add them to the next frontier. Okay? So we've done this before. We do for unsigned int edge is equal to CSR graph dot source pointers of vertex. Edge is less than CSR graph dot source pointers of vertex plus 1, and then plus plus edge. And disable the wrapping. Okay, so here I'm iterating over all the outgoing edges of the vertex. And then for each vertex, for each edge, I want to find, let's say I'm iterating over the neighbors of this vertex. I want to go over the edge. I want to find the destination vertex, and I want to check if that destination vertex has been visited or not. Okay, so I'm going to write unsigned int neighbor is equal to CSR graph dot destination of the edge. So I find the neighbor. Now I want to check if the neighbor has been visited. How do I do that? I check the level of the neighbor, right? If the level of the neighbor is uint max, okay, so here I know that the neighbor has not been visited. What do? I update the level of the neighbor. So I do level of neighbor is equal to the current level. Okay, so now I have marked the neighbor as being part of level 2. Now what I need to do is I need to insert the neighbor into the next frontier. How do I insert the neighbor into the next frontier? Well, I have the counter. Remember, I have the num current frontier counter. I am going to increment that. That's going to give me an index, right? And I'm going to insert the value at that index. Okay, so let me get an atomic reference to the counter. So I'm going to do CUDA atomic ref. The counter is an integer. And then what's the scope? All the threads across the device are updating the counter. So the scope is going to be the device, exactly. Okay, and let me call that num current frontier ref, and I'm going to give that the number in current frontier. Okay, so here I've created an atomic reference to the counter. The next step is to use this atomic reference to increment this use atomic reference to increment the counter by 1. So I'm going to do num current frontier underscore ref dot fetch and add. How much do I add? 1, right? And what's the ordering? It's relaxed, right? I'm not I'm not like setting a flag to indicate that some data has been written somewhere or waiting for some data to be written somewhere. So the ordering is relaxed. Okay, so when I increment 1 by the current counter by 1, I want to get the old value of the counter, because the old value of the counter is going to tell me where I can insert my vertex, correct? How do I get the old value of the counter? That's actually the return value of the fetch and add, right? So when I do fetch and add on a counter, right, the return value of fetch and add is going to be the old value right before I did the atomic add. Okay, so that tells me where I can insert. So here, I'm going to get the return value. Let me call that the current frontier index equals this, the return value, and then I'm going to insert the neighbor in the current frontier at that index. So current frontier of current frontier index is equal to neighbor. Is this clear?
Professor?
So what I did is I incremented a counter for the current frontier. Here called next frontier is the current frontier, and the thread will get the old value of the counter before it was incremented and insert the neighbor at that location. Okay. Yes, somebody had a question online.
Yes, I have a question. Honey, we're checking if the level of the neighbor is equal to uint max, but what if two threads do that at the same time? They're gonna both add the element to the list, no? And this would be
Yes,
kind of a
yes,
race condition.
that's a very good point. So the question is, so let's go back to an earlier level. Let's look at this level, for example. So here in this level, this thread is going to find this neighbor as being unvisited and mark it as being part of level 2. And concurrently, this thread might also find this neighbor as being unvisited and mark it as being in level 2. Now, before, when we weren't doing frontiers, that was okay, right? It's an idempotent operation. Multiple threads mark the neighbor as being the same level, no problem. But now, whenever I'm marking a neighbor as being part of the current level, I'm also adding it to the frontier. And adding to a frontier is not an idempotent operation. If multiple threads find this neighbor and multiple threads added to that frontier, what would happen is on the next iteration, the same vertex is going to be placed twice in the frontier, right? And then multiple threads will process that same vertex, and this can exponentially explode. Okay, so here we can't have multiple threads visit the same vertex as their neighbor. Only one thread should be allowed to visit the vertex. Is that clear? Okay, and if you want to see where that's happening in the code, so here, this is the code that we wrote. Basically, what we are doing is we're checking if the neighbor is not visited. And if the neighbor is not visited, we go and we mark it as being part of the current level. A race condition can happen here because if multiple threads are checking if the same neighbor are not visited, if one thread makes this check, and before it can update the neighbor, another thread also makes this check and goes in this if statement, right? They will end up both inserting the neighbor into the frontier. So here, the race condition is happening between this read of the uint max and then the writing of the current level. Okay, so to avoid this race condition, what do we need to do? We need to do something atomically. What should be done atomically? Right, we need to be able to atomically check if the value is uint max, and if the value is not, if the value is uint max, we want to go and set the value to the current level. Is that clear what this operation is? We call this operation a compare and swap. A very common type of atomic operation is a compare and swap, right? Or a compare and exchange. Okay, a compare and swap or compare and exchange is an atomic operation that compares two values or compares a value to some expected value, and if they match, exchanges it or replaces it with a new value. Okay? Any questions online? Any questions? Okay, great. So what we need to do is we need to have implement an atomic compare and exchange. What I'm going to do is I'm going to actually have a helper function to help me do this. Okay, by the way, I need to include CUDA atomic. I forgot to do that. Okay, what I'm going to do is I'm going to define a device function. And I'm going to call it visit vertex atomically. Okay, this device function is going to take the vertex that I want to visit. It's going to take the levels, and it's going to take the current level. And what the device function is going to do, it's going to check if the vertex, the level of the vertex is uint max, and if it is, it's going to set it to the current level, and it's going to do all that atomically. Okay? All right. And the return value is going to be whether this was successful or not. So if I successfully visit the vertex, I'm going to return true. If I'm unsuccessful, I'm going to return false. Okay. So the first thing is I need to get an atomic reference to the value that I want to update atomically. What's the value that I want to update atomically? The level of the vertex. Okay. So I'm going to get an atomic reference to that. So I will write CUDA atomic ref unsigned int. What's the scope? The device. Okay, let me call this level ref. And here it's the level of the vertex. Okay, now what do I want to do with the level of the vertex? I want to do a compare and exchange, right? So there's a C++ atomic function for this. I'm going to write level underscore ref dot compare underscore exchange. So compare and exchange does a compare and exchange. Now there's actually two flavors of compare and exchange. There's a strong version and a weak version. We're going to use the strong version. The weak version so the strong version, if they're equal, it always does the exchange. The weak version, if they're not equal, it won't do the exchange. But if they are equal, it may do the exchange, it may not. Okay, and this is useful in certain cases where we might be spin locking or have a loop around this compare and exchange. Don't worry about this. You're not worried. You don't have to worry about it. I just want you to be aware of the reason I'm using strong is because there's a weak version. Okay, so compare and exchange takes two things. Okay, well, it takes more, but we're going to start with two things. It's going to take the value that I want to compare to and the value that I want to replace if the comparison is successful. What's the value that I want to compare to? Uint max. And what's the value that I want to exchange if the comparison is successful? The current level. Okay, I'm not done, but is this clear? Any questions? Somebody had a question online.
Yes. Is the compare and exchange equivalent to something along the lines of a ternary operator?
Is it equivalent to a ternary operator? No, the ternary operator is usually it compares two things and then selects one of. Oh, I see what you mean. So yes and no, because the ternary operator can take an arbitrary condition. Here, the condition is just a comparison between two values, right?
Yes, that's what I meant.
Yeah. Okay. So any other questions about this? Okay, now there's a few technicalities here. One is that in some cases, so if the comparison is successful, that means that the old value was uint max and the new value will be current level, right? Now, if the comparison is unsuccessful, it means the old value is not uint max. Now, in some cases, the programmer might be interested in knowing what that old value is, okay? In our case, we're not interested. Okay, but in some cases they are, and that's why we need a way to get that return value back in order for us to check what it is. And that's why this uint max here is actually, I need to pass a variable by reference. I can't pass a constant like this, because if they are not equal, then this first parameter will be updated to include the old value. Okay, and this is useful if you're spin locking, because then the new value will become your new expected value that you want to check if it's equal to. So this is useful for other contexts where we might use a compare and swap. It's not really useful in our context, but we need to adhere to the syntax. So I'm going to define another variable. This is the expected value, and this is going to be uint max. Okay, and then I'm going to place this expected value over here. So in this case, if the old value of the counter of the level was not uint max, then this expected variable will be updated and tell me what is that new value going to, what was that old value. Is this clear? Okay, great. So now we've seen how to do a compare and exchange. Now there's a couple more things. I know it's very there's a lot of complications, but this becomes boilerplate code that you don't have to worry about a lot of the times. So we need to provide the memory ordering. Is the memory ordering in this case relaxed, or is it release, or is it acquire? Is it sequential? Is the compare and swap being used to wait for something else in memory that I want to read, or to tell somebody else that they can go ahead and read something? So, but there's a data dependence here. So yeah. So when there's a data dependence with other memory accesses, that's fine. What do we care? Is there an ordering with respect to other memory accesses where there is no data dependence? There isn't, right? So I have to do a relaxed, right? So I will do memory order relaxed. But actually, the compare and swap is actually two different atomic operations. There's the case where they're equal and the case where they're not equal, right? If they're equal, we're going to do an atomic exchange, right? We're going to do atomic store where we're going to store the new value. If they're not equal, we're going to do an atomic load where we are going to load the old value. And in some cases, we may want to have different semantics for if it's if it succeeds or if it fails, right? So that's why we actually need to provide two parameters for the memory ordering semantics. In our cases, whether we succeed or whether we fail, in both cases it's relaxed. Okay, so we're just going to provide relaxed twice. Okay, the first one says that if the compare and swap succeeds, the memory ordering semantics is relaxed. The second one says if the compare and swap fails, then the memory order is relaxed. Okay? Okay, great. So now I did my atomic compare and swap. Now what I want to do is I want to return if I succeeded or not. How do I know if the compare and swap succeeded? Well, it turns out that the compare and exchange function actually returns a Boolean that tells me if I succeeded or not. So that's nice and easy. I can simply write unsigned. Oops. Right, so here compare and swap tells me whether I succeed or not, and I simply return visit success. Okay, so here this function is going to do an atomic compare and exchange and visit the level. If it set the level to, if the level was previously uint max, it'll set it to the current level. Do I have a mistake somewhere?
Professor, shouldn't you pass the first variable by reference as a pointer, the expected?
No, it takes it by reference. So it's C++, so it takes a reference. It's a pass by reference.
Keep the return type.
Yeah, we can make the return type bool. We can keep it unsigned int. I'm going to keep it unsigned int. Okay. So now instead of doing all of this, here we can simply write visit vertex atomically, and we're going to provide the vertex, the level, and the current level. Okay? And this is going to take care of doing the compare and exchange and returning whether that compare and exchange was successful. Oh, you're right. So here I want to visit the neighbor, not the vertex. You're right. Thanks. Okay, clear? Any questions? Okay, let's compile and run. I hope we didn't make any mistakes because there was a lot of code that we wrote. Okay, so we're compiled. Now we can run it. And again, this is the push approach. So I'm running it on the road graph. Okay, it seems that the system, oh, there we go. Okay, so here it took 14 milliseconds. Do people remember how much it took last time? Oh, somebody does remember. So if you remember the push approach last time when we remember for the road graph, the push approach was the fastest, right? And here the push approach on the road graph when we did not use frontiers, okay, it was 25 milliseconds. So now we're down to 14 milliseconds. Okay, that doesn't mean the frontier base is always the fastest, right? On the other graph, the kind of scale free graph, the social network graph, the frontiers might actually hurt the performance. Okay. All right, great. So now we've seen how we can use these frontiers in order for us to improve the work efficiency and therefore improve the performance. Okay. Any questions? So, and this here is the code that we wrote. Somebody's asking, isn't it bad in the first couple of iterations? Well, it's just as bad without frontiers. It's even worse without frontiers because with frontiers, in the first few iterations, there's a very small number of vertices. You're only going to have threads for those vertices. Whereas without frontiers, in the first few iterations, you're going to have threads for all the vertices, and most of them are going to do nothing. Okay? All right. So here, this is the code that we wrote. What does this pattern remind you of? Have we done something like this before, where we kind of atomically increment a counter and then insert something into an array? What does it remind you of? Right, exactly. So this is the same pattern as the unstable filter. Okay, it's particularly the part where we are filling up this list by incrementing a counter and inserting things into that list. We did the same thing with unstable filter. Okay, so what can we do to optimize this? Well, it's the same things we did with unstable filter. How did we optimize the unstable filter case?
Privatization.
Right, privatization. So one thing we could do is also coalescing atomics, right? But we know the compiler already does that. So here, all the threads are incrementing the same counter. So threads in the same warp, we can do coalesced atomics so that we only have one atomic operation per warp. The other thing that we can do is privatization. In other words, instead of having every thread write to the global frontier or the public frontier, we can have every thread block have its own private frontier, insert things into that private frontier, and then write them to the public frontier in bulk using one atomic operation. So one optimization we can apply is frontier. So here all the threads are incrementing the same global counter, so we have high latency. This is similar to the unstable filter pattern, and we can apply the same optimizations. The first one is coalesced atomics, which we know how to apply, and which you also know that the compiler already applies. The other one is we can privatize the frontier and put the private frontier in shared memory. So in other words, here every thread block can allocate a buffer in shared memory for its private frontier. The threads in the thread block can do atomic operations on a counter in shared memory and do the random accesses to insert their vertices into shared memory. And then when every thread block is done, it can then go and write out their private frontier to the public frontier in the global memory. Is this clear? Any questions about this? All clear? Yeah? Okay, so do you want to implement this? Let's implement it. Although we already implemented something very similar, but you know, let's implement it just kind of as a review. Okay, so here, what we need to do is we first have to allocate a local frontier and shared memory for each thread block. Okay, so let's do that. So here we're going to initialize the local, or let me call it the private, because we're doing privatization, private frontier. So I'm going to initialize a shared, let me call it current frontier underscore s. I need to give it a size. Now in the filter pattern, every thread had a fixed number of elements. So I knew the maximum number of elements that a thread may insert. But in this case, every thread is going to iterate over a neighbor list, and I don't know how large the neighbor list of that thread could be. A vertex can have 1,000 neighbors, and all those neighbors might be unvisited. And if every one of these threads has 1,000 neighbors that are each unvisited, right, then I may not be able to allocate enough shared memory to fit all of those. So what I will need to do is I'll need to allocate a fixed amount of shared memory that doesn't hurt my occupancy, and then I'll have to check for overflow, and if I overflow, I can simply spill to the public frontier. Is that clear? Okay, so here I'm just gonna allocate some number, let's say 1,500. Okay, I've previously verified that this number will not hurt our occupancy. Okay, and then I also need to have a counter that the threads will atomically update in order for them to allocate space in this private frontier. So it's going to be a shared counter. Let's call it num current frontier underscore s. Okay, I need to initialize it to 0. Do I just do this? No, because this variable is a shared memory.
Every thread is gonna do
Excuse
this.
me?
Isn't it because every thread is gonna do this?
Right, exactly. So we only want one thread to do this. So how do we do that? We're just going to have one thread in the block do the initialization. Okay? And then, of course, all the other threads have to wait for that thread to initialize it before they start accessing the counter. So I'm going to have a sync threads over here. Clear?
Isn't this a benign race condition though? So it doesn't really matter if we do this or not.
It is. But remember, you have multiple warps. Because it's easy to control, it's better not to do it. Because you have multiple threads, multiple warps. All of them are going to do stores. They're going to interfere with the stores. The hardware is going to have to absorb all these stores. So it's better for performance to just have one thread do it. Okay? Okay, now we're going to perform the actual BFS. Okay, so same thing. Every thread takes a vertex in the frontier, it iterates over the edges, gets the neighbors, visits the vertex atomically, and if it succeeds to visit the vertex, now what we need to do is we need to add to the frontier. So this code over here is adding to the public frontier. I don't want to do that. I want to add to the private frontier. Okay, so let me do that. First, I need to atomically increment the counter in shared memory. So I need to get an atomic reference to that counter. So I'm going to do CUDA atomic ref unsigned int, and then what is the scope? The device? It's the block, right? Because only threads in the same block are going to be incrementing this counter. So here the scope is the block, which allows us to have allows the update to be faster. Okay, so the block, and then let's call this long name. You can call it something shorter if you want. I like using long and clear names, but some people don't, and it's just a matter of style. And this is going to be a reference to the counter in shared memory. Okay? All right. So now that we have an atomic reference, we're going to increment that atomic operation. So num current frontier underscore s underscore ref dot fetch and add. How much am I going to add? 1. And what's the ordering? Relaxed. Okay? All right. Now, if I succeed, then it's going to return to me the index where, sorry, not if I succeed. This succeeds, right? It's not a compare and swap. Okay, so now it's going to return to me the old value of the counter, which is the index where I want to insert. So I'm going to write, so this is going to be current frontier index. I'm going to write underscore s, not because it's in shared memory, but because it's the index into the one that's in shared memory. Okay, and now I can use this to write to the shared memory frontier. So current frontier underscore s of current frontier index underscore s is equal to the neighbor. Okay, but can I always do this? No, I need to make sure I didn't overflow. In other words, I need to make sure that the index is less than 1,500. So I'm going to do if the current frontier index underscore s is less than 1,500. Probably better to have a macro doing all this. Then in this case, we're going to insert in the current frontier. If it's not, what do we do? Well, we do this. We're going to go and insert into the global memory. Of course, we also need to restore the old value of the num current frontier, right? So I can go back and I can do num current frontier underscore s is equal to 1,500.
Why do we need to restore the number? It doesn't matter.
So because later on when we want to write this frontier from the shared memory to the global memory, we need to make sure that we have the right size. So we can restore it here, or if we want, we can later check, and if it's greater than 1,500, we can just use 1,500. Either is fine.
It's a race condition, no? Command?
Yes, this is a race condition. You're right. So it's probably better if we just at the end check. Of course, that risks that you might overflow the counter, but here the counter is large enough, then chances are you're not going to overflow it because you don't have more edges in the graph than the range of an unsigned int. Okay. All right. So after we are done with the BFS, now we have our frontiers in the shared memory, so we can sync threads, wait for all the threads to finish inserting the current frontier. Now what I want to do is I want to go and take this local frontier and write it to global memory. Okay, so to do that, first I need to allocate space in the global memory. How much do I allocate in the global frontier, the public frontier? The size of the private frontier, exactly. So I'm just gonna have one thread do this. So here we're gonna allocate in the public frontier. So only one thread in the block should do this. Okay, and it's actually very similar to the code I have over here. So I'm going to get an atomic reference to the counter of the public frontier. That's the first line. And in the second line, I'm going to allocate. I'm going to do a fetch and add, but instead of adding one, what am I going to add?
Num current frontier s.
Num current frontier underscore, the size of the private frontier. And that's going to return to me not just an index, it's going to be returned to me the index of the first element. So this is the start element where I'm supposed to write the entire private frontier to the entire public frontier. So let me call that current frontier start. Okay, great. Now, after I do that, then I want to go and I want to write this value from the shared memory to the global memory. So I should do this in parallel, right? So thread 0 will write element 0, thread 1 will write element 1, thread 2 will write element 2, etc. So to do that, all the threads need to know where this buffer starts. Okay, so now after thread 0 has done this allocation, it should communicate this start. Don't know why I put an X there. I should communicate this start to the other threads. So instead of putting it in a register, I'm actually going to allocate this in shared memory. Okay, and now I will sync threads here so that all the threads finish for thread 0 to finish allocating before they start using it. Okay, now I can write the private frontier to the public frontier. How do I do that? So I can
check
do
if
if
the
thread
index is
index is
less than
less than num current frontier size, but the problem is that the size of the private frontier could actually be larger than the number of threads, right? Because every thread might insert more elements than more than one element. So I actually have to loop, right? So first thread 0 will do element 0, thread 1 element 1, thread 2 element 2, etc. But then they have to, next iteration, they have to move them all by block dim, then move them all by block dim, then move them all by block dim. So I'm going to have a loop over here. We're at 4 unsigned int current frontier index underscore s. So this is basically the index into the current frontier, right? So somebody's asking, can we do an atomic add of the minimum? Yes, between the size and the counter, and yes, we can do that. Okay, so here this initially thread index dot x, and then we keep iterating until we reach the total size of the private frontier, and every iteration we increment by the block dimension. Okay, so here current frontier index underscore s is the index of the element we're writing in the private frontier. Okay, we need to write that to the public frontier. So we're current frontier of something equals current frontier underscore s of current frontier index underscore s. Okay, is that clear? What is that something? Where do I write in the current frontier? Well, I'm going to write to the start plus the current frontier index underscore s. Exactly. So here, my current frontier index is basically the current frontier start. This is the value that I got when I did the atomic add up here. Okay, and then I add to that okay, and then I will use this current frontier index right here. Right, and this is how we can apply privatization to the frontiers. Any questions?
Shouldn't we check the
Somebody's asking how we knew the starting location of each of these private things in the global memory. That's what this line over here did. Right? One thread in the block allocated a chunk in the global memory, and this is the start index of that chunk. So what about the overflowing ones? The overflowing ones were probably allocated here at the beginning. Yeah? Okay. Somebody online has a question?
shouldn't we check that the threads inside the loop are like, should we include a boundary check?
Well, the boundary check is already implicit in the loop loop boundary check, right? So here in the loop bound, we already have this boundary check.
All
Okay.
right.
All right, so we compile. Let's hope we don't have bugs. Okay. And we run. Okay. Oh, it's not supposed to be slower. I think that's just a glitch. Okay, I don't know why it's slower. Maybe there's some noise on the node. It's faster. It's supposed to be faster, but it's only a little bit faster for this graph. Okay, but for other graphs where we might have larger private frontiers, it could be significantly faster. Okay, great.
Professor,
So
you were
here,
looking at the time without the frontiers, at the time of the normal pull, I think. That's the time, the 25 milliseconds one is the time of the normal pull, not the one with frontiers.
yeah. The time without, that's what I'm saying. So the time without with the frontiers was 14 milliseconds. So I don't know why these are coming out to be 15 and 16. There we go. Yeah, it seems there's some instability in the measurement. Okay. Anyways, so let's move on so that we don't run late. So this here is the code that we wrote. So any questions about frontier privatization? All clear? Okay, great. So so we've optimized our code, but now that we're doing these frontiers and we're running on a road graph, so the frontiers are actually small. So we have a lot of these levels, a lot of iterations, and every iteration is doing a small amount of work. Okay, so what do you think now it might become a major overhead? Every iteration is a kernel that I launch. So I'm launching many of these kernels, and each kernel is doing a little amount of work. So now what becomes an overhead? The actual overhead of launching the kernel, right? When the kernel does a small amount of work, the amount of time it takes to just launch the kernel could become a significant amount of the computation. And if I'm launching a lot of these kernels, I incur that very frequently. Okay, so I have a problem now, which is this kernel launch overhead. All right, now why am I launching all these kernels? It's because I need to wait for the previous levels to the thread. I need to wait for all the vertices in the frontier to be enqueued before I start consuming them, right? I can't go and start visiting a new level before the previous level is done, because I might end up visiting an old vertex that would have been visited before. So I have to wait for the previous level to finish before I start the next level. So the objective of this launching a kernel for each level is to make sure that we finish a level before we're starting a new one. So we need to perform a barrier synchronization between levels. And the objective is for threads to wait for all the vertices of the current level to be in the frontier before they proceed to the next level. So far, what we've been doing is we're launching a new grid for every level. And here, this incurs the overhead of launching the grid. It also incurs the overhead of having to, you know how we're copying this counter to know if we need to keep iterating or not, right? Every iteration we copy to check, we copy the counter to check what is the size of the frontier to know if we should launch another iteration. So all this incurs overhead. Now, if I want to avoid this overhead, what can I do? Something we haven't seen before, but something that I've mentioned before. We want to do a synchronization across all threads in the grid. And we can do that with cooperative groups. So an optimization that we can do is, instead of launching a kernel for every level, we can launch one kernel, and we can iterate over the levels inside of that kernel. And after every iteration, we can do a grid-wide barrier synchronization. So we can use the cooperative groups API to perform a grid-wide barrier synchronization in between levels, and then that way do the whole thing in just a single grid. But what's the caveat with grid-wide barrier synchronization? We mentioned this before. To be able to do a grid-wide barrier synchronization, what do I need to guarantee?
There's a limit on the grid.
That what?
There's a limit on the number of blocks.
Right, there's a limit on the number of blocks in the grid. I cannot launch more blocks than the number that can run simultaneously. Okay? Huh?
So it will limit the size of the graph.
So it will limit the size of the graph, or we'll have to do something else. So we'll see. Okay? So what this does, it requires launching no more than the number of blocks that can run simultaneously. And so far I've been mentioning this, but today we have a nice example where we can actually do it. Okay? So let's see how we can do this. Let's see how we can limit the number of blocks to be the number of blocks that can run simultaneously. Right, and then use the cooperative groups API to do a grid-wide barrier synchronization within the grid. Okay.
Launching a new grid that much more expensive than a grid-wise synchronization?
Yes, it can be.
Okay.
Okay. So first of all, to use the cooperative group API, we need to include this right here. So I'm actually gonna to make this quick, I already implemented some of the code for us. So here I've already included this cooperative groups. I included this header so that we can use it. Okay, and then to be able to calculate the number of blocks that can run simultaneously, I need to calculate two things: how many SMs do I have, and how many blocks can run on the SM. Okay, we calculate each of these separately, we multiply them, we get the total number of blocks that can run. So how do I find out the number of blocks that can run per SM? So this code right here helps me do that, right? This function, CUDA occupancy max active block per multiprocessor. This function, I give it a kernel, and I give it the number of threads I want per block, and it returns to me the number of blocks per SM. I can also give it how much shared memory, dynamic shared memory I want per block. Okay? So this function right here, we can call it, and it tells us how many blocks can run per SM. So actually, I have that in the code down here. So down here, notice I'm calling CUDA occupancy max active blocks per multiprocessor, and it's telling me the number of blocks that it can run per SM. To calculate the number of SMs, we saw this in lecture 2, for those of you who remember. No, lecture 4, I think, for those of you who remember, chapter 4. So you can basically query the device properties, and in the device properties, you can get the multiprocessor count. That's the number of blocks per SM. Okay, and then to find the number of blocks that can run simultaneously, I simply multiply those two things. And then to be able to use the cooperative groups to launch this kernel, I have to actually use a special function, CUDA launch cooperative kernel, and I have to pass the parameters in as a separate array. So there's just boilerplate code that you can use, okay? And this code is what I'm using right here. So up here I'm defining an array that has all the arguments, and then down here I'm doing CUDA launch cooperative kernel to launch the kernel. Okay, is this clear? Any questions? Okay, and I know that we're running out of time, so by show of hands, do you want me to implement it, or should I just show you the code for it? Okay, so I'll implement it. For those of you who need to leave, feel free to leave. Okay, so let's do the implementation, because we haven't used cooperative groups a lot, and I would like to show you how it works. Okay, so now this is the kernel that we had before, and before this kernel was only doing one level. Okay, now what I want to do is I want to have the loop over the levels inside this kernel, and then after every iteration, I want to do a grid-wide barrier synchronization. Okay, so the way to do this is as following. First, we need to get a handle on the grid. That's very easy. We simply do grid group grid equals this grid. So let's do that. I'm going to come here. I'm going to write grid group grid is equal to this grid. So this gives me a handle on the grid. Now, what can I do with this handle on the grid? I can get the thread rank. This is the index of the thread within the entire grid. I can get the number of threads in the grid. That's before we used to do that with griddim.x times blockdim.x. Okay, and most importantly, I can call grid.sync, and grid.sync will do a grid-wide barrier synchronization across the entire grid. Is that clear? Okay. Okay, so now we have all the ingredients that we need. What we're going to do is we're going to have a loop across all the levels. So I'm going to write for unsigned int current level equals, remember we started at 1, not 0, because 0 was already the source vertex, right? And then we keep iterating until the number of elements in the previous frontier is greater than 0, and then each iteration we increment the current level. Okay, and I'm going to go all the way down here, close this loop. Okay, all right, now what do we do in each level? So in each level, well, we're going to do the same things. We're going to initialize the frontier. We're going to perform the BFS, but now we have a problem in performing the BFS. What's the problem? I don't have as many threads as I want. My number of threads is limited, correct? Right, because we limited the number of threads per block to be the number that can run simultaneously. But my frontier could be larger than that. So what I need to do is I need to have the threads iterate until they consume the entire frontier. So instead of just doing I equals blockindex.x times blockdim.x plus threadindex.x, every thread will first process this, but then every time they will increment by the total number of threads until they've consumed everything. So I'm going to do for unsigned int this equal I equals blockindex.x and blockdim.x plus threadindex.x, and then I keep iterating as long as I is less than number of vertices in the previous frontier. And every iteration I increment by how much? 5. the total number of threads in the grid, that's block dim.x times grid dim.x.
Can't we get this from the grid itself?
Right, exactly. So as I told you before, some of the nice things that the grid gives us is the thread rank, the rank of the thread in the whole grid, and the number of threads in the grid. So what we can do is, instead of writing all this jumble, block index.x times block dim.x plus thread index.x, that we've been writing in almost every lecture in this class, I could simply write grid dot thread rank. That's another nice thing about the cooperative groups API. If I don't care about distinguishing between blocks, I just want to deal with all threads in the grid, I can use this cooperative groups API to make my code simpler. And here, instead of writing block dim.x times grid dim.x, I can simply write grid dot num threads. Okay? Okay, great. So then I do this, I do my BFS, and I do the allocate in the public frontier, and I write everything to the public frontier. And now what I want to do is I want to synchronize. Okay, how do I synchronize? Well, it's simple. I do grid dot sync. Okay, so grid dot sync will do a barrier synchronization. But there's another thing that I need to do, because on the host, other things I need to do was I was swapping the frontiers, right? I was doing double buffering where the current frontier becomes the old frontier becomes the new current frontier. So I need to swap the buffers, and I also need to swap the counters, right? Because now the number in the current frontier has become the number in the previous frontier, and I need to initialize the number in the current frontier to 0. So here I'm going to do num previous frontier is equal to num current frontier, and then num current frontier is equal to 0. Okay, and then now I can go. But I actually need to do a grid sync here, right? Because I need to make sure that all the threads finish reading the old counter before I clear it to 0. Okay, so I need another grid sync right here. And I also need to make sure that all the threads finish clearing this counter. Actually, all the threads shouldn't finish clearing this counter. Only one thread should clear this counter, correct? So I should surround this by if grid dot thread rank equals 0, num current frontier equals 0. And then now I need to make sure that all the threads in the grid wait for the first thread to finish clearing the counter before they move on. So I can do another grid sync. By the way, I can get rid of these grid syncs by pre-allocating a counter for every level. So if I pre-allocate a counter for every level, rather than using the same counter, right? I can get rid of this. This is a false dependency here, right? The only reason I need to do these syncs is because I need to wait for them to read before I overwrite, correct? So if I don't want to do this, I can simply pre-allocate a counter for every level and initialize them all to zeros, and I can get rid of these grid syncs. But I'm being a little lazy now. I don't want to do all that. So how do you know how many levels we have? You can just, I mean, you can have an approximation, or you can just allocate something that's as large as the number of vertices. You can have some bound. Okay. And another thing I need to do is I need to swap the previous frontier and the current frontier buffers. So that's easy. Temp is equal to previous frontier. Previous frontier is equal to current frontier, and then current frontier is equal to temp. Okay, and by doing this, now I have only one iteration, and now I'm iterating over the levels within the kernel, and I'm synchronizing between the levels after every iteration. Let's hope we wrote this quickly, so let's hope we didn't make any bugs. But as you can see, the code is not that complicated. Okay, the host code is a little complicated, but the code is not that complicated. So let's compile and let's run now and see how this performs. And as you can see now, we're down from 14 milliseconds to 8 milliseconds. So you can see that once if we do this, by the way, for the one that wasn't using frontiers, we will not see this much benefit. But now, after we use the frontiers, each one of the kernels was so small that the kernel launch overhead was killing us, and we were able to cut it almost in half by getting rid of that kernel launch overhead. Is that clear? Any questions? Okay, so this is the code that we wrote, and that is all for today. We're done talking about graph traversal, and next time we'll start a new chapter. Bye, everyone.